Morning, students. Last class, we rather analyzed the performance characteristics, a number of performance characteristics of a half-wave rectifier. Today, we are going to do the same exercise for full-wave rectifier. And exercise steps and equations will be same, but results will be different. Side, you see your picture of the full wave rectifier where there are two secondaries and each secondary has a peak voltage of Vm, and, and in both half cycles of the primary, the current flows through the load in the same direction. So when this is the primary waveform, the secondary waveform is like this. Each half cycle, it becomes a positive half cycle. Okay, that's that. We know that. Now let's see how it performs. Right? First, we shall go into transform. Here a center tap transformer is needed. Also, the secondary is equivalent to two secondary coils. Hence, of course, the transformer will be costlier. This is number one. Number two, transformer secondary rating. As I said earlier, transformer secondary rating is always expressed in terms of RMS voltage of the secondary. Here, each one has Vm, and Vm by RMS voltage is Vm by root 2, which can be called V. And so the total secondary RMS is 2V. So here the transformer will be costlier. There are two secondary windings and their total secondary RMS voltage is also 2V. That means transformer capacity is much larger. Next is number of diodes. You need two diodes. So cost of the diode is more. And diode PIV. Diode PIV in a half-wave rectifier was Vm. Now here it is 2Vm. How it is 2Vm? Let me show you that. It is 2Vm. Let me show you that. Say any positive half cycle, this is a positive half cycle, and here is a negative half cycle. And positive half cycle current flows through this, and so this diode is forward biased. But this diode is reverse biased, right? So what is the voltage across this diode? Maximum reverse voltage. At this highest point, the voltage here at this point is Vm. And since this is reverse biased, here the voltage is minus Vm. So what is the maximum reverse voltage across this non-conducting diode? Is 2Vm. So you need two diodes first thing, then each diode, the PIV should be double, so diode will be definitely costlier, right? Then what is the output DC? Output DC, of course, will be double of what we got in half-wave rectifier. In half-wave rectifier, output DC was Vm by pi. Here, if you do the same integration, it is 2 Vm by pi. Here, you integrate over pi, 1/2 cycle, and then average is 1 by pi. So it is become 2 Vm by pi. So this is one great benefit. Your output DC is double. If in the same type of half-wave rectifier you get 5-volt output, here you will get 10-volt output. Next, Output RMS voltage. Here, I have shown you the whole calculation, although you should be able to do it yourself, but I have shown you the whole calculation. RMS voltage is always the instantaneous voltage equation, Vm sin omega t whole is integrated over a time duration 0 to pi and then averaged over pi, right? Because it is the same thing repeated. So if you integrate over pi, average over pi. So this is becomes Vm square, Vm goes outside, Vm square by pi. This is sine square omega t d omega t. Sine square omega t is 1 minus cos 2 omega t by 2. So this 2 you take outside, so it becomes Vm square by 2 pi 1 minus cos 2 omega t dt. Its integration is integration of 1 with respect to omega t is omega t minus sine 2 omega t by 2. Now, when you put the limits 0 to pi, sine 2 pi into pi is also 0. This sine 0 is also 0. So you are left with only omega t, which upper limit is pi. So Vm square by 2 pi. So it is Vm square by 2. That is RMS square. So what is your RMS? Is Vm by root 2. Right? Next we go to, so we got output DC, we got output RMS. Now, between DC and RMS, there are some criteria relations that we shall find. What is the ripple factor? Is the ratio of AC square by DC square. That is ripple factor square. And ripple factor is AC by DC. So VAC square is RMS square minus DC square. Same way, it is VRMS square by VDC square minus 1. VRMS and VDC, both values we have got. If you calculate this, this becomes ripple factor 0.483. Do you remember the ripple factor of half-wave rectifier? Ripple factor of half-wave rectifier was 1.21. That means for 10 volt DC, you have to have 12 volt, 12.1 volt AC. It was very poor. Here in full wave rectifier, for 10 volt DC, you have 4.83 volt AC. That means much, 3 times less, 1/3 of half wave rectifier. So if you compare the non-desired AC component, of course, full wave rectifier is much better. Then comes ripple frequency. This is a full wave waveform. If you find out its Fourier expansion, it becomes this, right? I do not want to deduct the Fourier expansion. That becomes a lengthy deduction. And here, the fundamental frequency of the AC is 2 omega 0, which was only omega 0 in case of half-wave rectifier. That means if you are using it in domestic power supply frequency is 50 hertz. So your fundamental AC frequency will be 100 hertz. That makes filtering of it very much easy. As I said in my last class, the lower is the frequency that you want to filter, the more difficult is the filter design. So remember this point, the ripple frequency of full wave rectifier is 2F0. Now, next point is form factor. Form factor is, once again, as we have seen earlier, form factor is VRMS by VDC. If you put both the values, form factor is 1.11. Next is, let us see what is the efficiency of this rectifier. Efficiency is VDC square by VRMS square, which is 81%. Do you remember what was the efficiency of a half-wave rectifier? It was only 40%, only 40%. Here it is 80%, right? After efficiency, we go to transformer utilization factor. Here, the transform utilization factor equation is little difficult because of these two secondaries and one primary. I have written it here. Here, the primary conducts for full cycle and each secondary conducts for one half of the cycle. Hence, transformer utilization factor for primary and secondary are different. So, what is the transformer utilization factor of the whole transformer? We always take a practical average. Now, let's see how we calculate this average. Ratio of this transformer is 1:1. That means input primary turn number of turns say 100, and each secondary is also 100. For example, 1:1. RMS voltage across the primary is, our primary voltage was Vm sin omega t, so its RMS is Vm by root 2. And so what is the RMS current? Is Vrms by RL, that is Vrms divided by root 2 RL. This is the load resistance, right? Now, so what is the VA rating of the primary? It is voltage Vm by root 2 multiplied by the current Vm by root 2 RL, that is Vm square by 2 RL. So that is the VA rating of the primary, on which primary cost will be decided. Then what is the transformer utilization factor of the primary? Transformer utilization factor is the ratio of DC power delivered by VA rating of the primary. What is the DC power delivered? VDC square by RL. And what is the VA rating of the primary? We got it here. If you put these values, you get transformer utilization factor of the primary is 0.811. That means 81.1%. So this is so far as the primary is concerned. Now let's go to the secondary. A full wave RMS current is Vrms by RL. Right? Is the Vrms appears here by RL is the full wave RMS current. And this current is provided by not one secondary, but by two secondaries. So, current given by each coil is Vm by 2RL, Vrms by root 2RL, which is equal to Vm by 2RL. And RMS voltage of each secondary coil is Vm by root 2, because this is the Vm appears here, peak value, Vm by root 2. So we got the current and voltage of each primary. Once we got current of voltage of each primary, therefore VA rating of current and voltage of each secondary, VA rating of each secondary is Vm by root 2, this voltage, and Vm by 2 RL, this current, is Vm square by 2 root 2 RL. So we got the so we got the VA rating of each secondary. And what is the transformer utilization factor? DC power delivered by VA rating. So we go to the next page. When you go to the next page, then you find, so transformer utilization factor, this comes from the earlier page. I have put it here. Transformer utilization of primary was 0.811 and VA rating of each secondary was this. Now come to this page here. Also, VDC is 2 Vm by pi, which is delivered by two secondary coils. So VDC by each secondary is Vm by pi, right? Then we can find out power DC of each secondary is V square by R is Vm square, it is Vm square by pi square divided by R. So we got the power delivered by each secondary. and here we got VA rating of each secondary. Then we can find out the transformer utilization factor of each secondary. So transformer utilization of each secondary is power DC of each secondary by VA rating of each secondary. That means Vm square by pi square RL divided by this value, VA rating of each secondary. If you do this, if you become 286, 0.286. So what do we find? We found here utilization factor of the primary was 0.81, 0.811. Utilization factor of each secondary is 0.286. Then how do we make the average? So transfer utilization of both secondary together is 2 multiplied by 0.286 is 0.572. Then we got the total transfer utilization factor. Primary 0.811 and two secondaries 0.572 and their average 0.691. That means transformer utilization factor of the rectifier is 0.691 or 69.1%. Remember, transformer utilization factor of the half-wave rectifier was only 28.6%. So, half-wave rectifier was really not so good, right? In next lesson, we shall do this analysis for the bridge rectifier. Okay.